Well, this is going to be pretty interesting group of people once again. I've got to say, I keep thinking of Eiffel and Erwin Hauer, who was my sculpture instructor at Yale, and Gaudi, and I think they would just be transported by this conference. I just think it's an amazing occurrence, and I'm so glad to be here. It's my job to introduce these people. The guy hunched over there on the table is busy writing his new book. He is probably the foremost proselytizer of the work that we all admire so much, and really kicked off, I think, with his embryonic architectural book, the interest in this formal language, and gave it legitimacy and provided an intellectual foundation for it. I'm speaking of Greg Lynn, and he spent some time at the Angevante, which I can never pronounce. I don't know, are you on your 6th or 7th book at this point? 8th one at that table, but something like that. So he is really, I think, a kind of catalytic force in bringing together all of us and providing a mutual language for us all to use. So we're very glad to have him here. He's also my former boss's spouse. Is that right? Former.
I'm still an employee of something.
Oh, you're still right. I'm an employee of Ming's. So that works, right? Over there on the table is Peter Testa, who joined SCI-Arc, I guess, in about 2005 or so. Coming from MIT, and again, numerous books and articles. I remember Peter's carbon tower, which is what first grabbed my imagination. If you can imagine a kind of spider web of carbon filaments being woven, actually, in space to produce a 30 or 40-story tower. I don't know how high you could go, but I think that was again one of this sort of fundamental explorations of a combination of building technology and materials usage, which has transported us all. And he's had a bunch of grants. I don't know how you get all of those. I mean, a bunch of Graham grants, and one I can't pronounce at all, called the Gulbenkian Foundation grant. They sound like a pharmaceutical country, but I think actually there is probably a coincidence between pharmaceuticals and architecture at this point. It's probably probably happening. I mean, I look at some of Hernan's work, and I'm sure there is. And then we also have Bill Pearson over there. I guess Bill and Greg share broken dreams because he managed to pop one of Bill's sails on his boat. Bill makes carbon fiber sails, which are all of one piece, and I think crumple and then go pop. Is that right?
I just didn't know what I was doing.
Okay. Anyway, they go fast, and I think you have literally been around the world in a race. That's pretty astonishing. So we've really got a hands-on person there that is dealing with all these materials in a first-hand way and then testing them with his own body in the middle of the Pacific Ocean. So I think that's pretty cool. So I'm ready to sit down and watch the launch.
Well, Marcelo, thank you very much for this conference. It's been a great morning. I hope it's not downhill from here. I doubt it. I thought, though, that I'm not going to really talk about materials or manufacturing processes so much. I know I'm supposed to, but I actually have nothing to contribute that hasn't been shown or is about to be shown. So instead, I thought I would talk a little bit about let's say a design sensibility or even an aesthetic that comes with a shift to composites. I think this doesn't have so much to do with materials per se, but just how we think about assembly and design and form. And it does affect how things get manufactured and put together. And I would just say that in my own approach to design, just because I think about composites, I don't throw everything else out. And just because I think about this sensibility of composites doesn't mean that I throw away another sensibility. Actually, more and more, I like to play things against each other in terms of design. But so as a kind of straw man that we're going to knock down, I'd like to put up this idea of intricacy and tectonics. Now, for me, the term tectonics, which is a term that architects love and love to use, is really about the mechanical assembly of parts. And architecture, probably more than most fields, deals with the most number of parts and the management of parts and how they get put together. It's inevitable that we're going to have to deal with tectonics. However, the more I know about composites, the more I hate things like screws, nails, bolts, all this stuff. I mean, it's incredible. You see somebody come with $20,000 of stainless steel bolts on the back of a truck that weighs several thousand pounds. It makes me crazy. You know, I'd rather have glue. Like, I'm a big, big glue fan. But so intricacy and tectonics, I mean, here in the drawing of Semper, even though Semper was talking about textiles, which I think is one of the things everybody's been talking about today, the textiles are assembled in layers and in hierarchical systems. So you have primary structure, you have secondary structure, you have cladding. I think this is part of the building industry and it's part of this tectonic paradigm, but it's all about mechanically attaching different systems one to another in hierarchical layers. That's why architects fetishize details, which the details are always about where two disparate things come together, like a wall and a floor, structure and cladding, you know, glass and a frame. So that's how you think about details when you think about tectonics. And this, for me, which was the first digital building I ever designed, was all about expressing digital variation in tectonics. And this is where this term intricacy, I think, is important. I think this is a discussion I'm looking forward to having with Evan about that, because this is not about surfaces and intricacy. This is about tectonics and intricacy. So every piece of structure, every interior panel, it's all different dimension, unique shape and size, but all related one to another in a series. It's a digital approach to a very old paradigm of construction. So for me, I'd like to talk now a little bit, instead of this kind of intricate tectonics, which comes out of a digital approach to construction, another kind of approach that comes out of digital design and construction, which is language of surfaces. And the first idea for me is surface minimalism. And this is it's a banal idea. It came out more from product design. But when you design a chair or something, if you use the intricacy idea, it's very odd to go to a company like Vitra or something and say, well, I got this computer and I can make all these different shaped parts and I can make complexity, and I've figured out a way to take what you build in 10 pieces as a chair and build it in 10,000 pieces. You know, they don't like to hear, they don't call that innovation. They say, you know, I've got a thing that you build in 10 pieces, I can build in 2 pieces, then they think that's innovation. So it kind of all started with this Visionaire case, which was a case for a book, but we eliminated the hinges and clasps by modulating the surface with these teeth so that it would all bite together and close and stay closed by the shape of the surface rather than by these pieces of hardware. So this is where I first had the idea, eliminate hardware and mechanical methods of attachment in favor of surfaces. So with the ravioli chair, bucket chairs had been done before, but we used this three-dimensional knitting machine to knit a contoured top, which has 3 different layers of foam glued to it. And then we incorporated all the legs into the base. So even though it looks like it's 2 surfaces, a soft surface and a hard surface, there's a little more going on in terms of the construction, but it was really an attempt to integrate components into surfaces. So instead of having legs and arms and a back and a seat, everything gets integrated into a language of ergonomic surfaces. And a lot of what I'm showing really has to do with ergonomics and the position of a body in a space. With the titanium Alessi coffee and tea set, same thing. I was told by Alessi, you know, architects don't put handles on things. Make sure you put handles on your coffee pot because architects hate that. And so as a challenge, I kind of made a handle surface and a container surface. So this is a superformed titanium. But the titanium is just in 4 sheets to make one of these coffee pots. So the 2 inner sheets are welded together and hold the hot liquid, and then there's 2 sheets on the outside that are held off with silicone, which let you grip it anywhere without burning your hand. But so integrating the handle, the thermal layer all into surfaces was another idea of this. And also, the texture and color worked with the voluptuous curvature and surfaces rather than working with, say, the detail of the handle to the pot, which might have been where previously you would have put your design effort in the detail. You know, and onto these cups, same deal. Okay, so what I've learned, not just in terms of form, but in terms of construction, is that if the tectonic paradigm is about mechanically attaching disparate parts one to another, the composite paradigm is about putting disparate elements into a bag or on a mold or both and cooking them together with a matrix. So instead of thinking of layering as a series of layers that are mechanically attached one to another, you're thinking about some kind of a mixture of elements that get bagged. Again, the tectonic examples in a boat. I mean, boats used to be built like houses. Cars used to be, still are actually built like houses. They have things on them. Actually, naval architects still call the part you live in on a boat the cabin. And actually, most of them look like cabins. But the tectonic paradigm here is of a series of elements that get assembled sequentially and skinned. Same thing with a car that's a few years old. It's a tectonic car. The idea of the bag really means that you're dealing with two skins and a core usually, often with different orientations of fiber and reinforcement, and also with all kinds of transitions glued and welded into that matrix. So this example of a more contemporary boat, I would just point out not so much the monolithicness of the surface, but the fact that you can't see a single bolt or piece of hardware. So the way these things are put together is with soft loops and connections, with integrated connections, all of the way that the rigging, the standing rigging, as well as the running rigging, is all integrated into this surface bagged and cooked so that you don't put things together anymore with metallic connectors primarily. I mean, only because in the world of weight and performance, metal is really like the worst thing you can ever bring on to a boat. The whole monocoque thing, I just want to point out, boats are like built with bulkheads. They're actually working with structural principles very akin to the way we think about frames and egg crates and skins and things. So they're stiffened with these elements, but again, they're all glued. I mean, to me, that's more important than the form, is the fact this is 100% glue, resin, matrix, and fiber. There's really not discrete elements being connected tectonically. Okay, and then, you know, to go back, a lot of this stuff comes from someplace in architecture. I mean, this is Osplin's kind of waiting room outside the crematorium in Woodlawn Cemetery, which I've always thought was amazing, the way he integrated the bench into the bent ply, or integrated a bent ply bench into the plywood thin ply skin. And this particular image really inspired me a lot for the interiors of the Bloom house that I'll show you in a second. Okay, so, you know, integrating components into a surface and integrating furniture into surfaces is, you know, part of this composite logic. I just brought some boats, mostly just to show Bill, because he's never seen them, I don't think. This is a Suncat, a open catamaran that I'm designing for the Tourism and Development Corporation in Abu Dhabi, along with a naval architect in Long Beach, Fred Krubla. And really, I mean, for me, the boat industry is the most interesting industry for architecture right now, mostly because their budgets are, in fact, not unlimited. I mean, they're a tenth the cost of an aerospace project if they're working with a carbon skin or something, maybe even less. And the innovation pressure there is very, very high. So there's a lot going on there. And in fact, the budgets are just like a building. I mean, it's incredible. If you measure this Suncat in plan, it comes in under $1,000 a square foot. I mean, for a balloon frame house, you can go out and buy a very bespoke boat with carbon fiber and Nomex and all this stuff. It's really incredible. I mean, I know they think their budgets are really high, but you should take them and show them what you get for $1 million for a house here in Los Angeles. So anyway, I've been playing around with everything from here up with boats with this friend of mine, Fred. So this, instead of having a cabin like a little hut, is a kind of a flying carpet of carbon fiber that provides shade for sailing around to one of the islands in Abu Dhabi. And the interiors also, usually you get on one of these high-tech carbon boats, you go down below and there's like a lot of wood veneer and even worse, brass and things like that. So I'm trying to rethink some of the way the insides of these things work. And this is a boat I'm actually doing for myself. It's a trimaran. And the inside of it, you know, is, because these things are never flat, you know, there's really no reason to make interiors like you have in your house. It's much, you know, it's a more dynamic interior environment. When you think about structure in these, which Bill is going to talk about, this is a product that Bill makes and invented, you often talk about laminate schedules and the orientation of fibers. But again, when they get cooked together, you get these amazing patterns, but very, very thin, lightweight constructions. And I know 10 or 15 years ago, when the Prada America's Cup campaign came out, they used images of their sails to market. And in all the design magazines, I saw these Prada sails, and I know Renzo Piano and all kinds of architects saw this stuff. I would assume Peter saw it then too. We all got inspired by this image of a woven shape. But what also inspired me is it's not a tensile shape. I mean, when I see those Fry Auto images, I go insane because I hate tensile materials because they're only one form and you don't get to design it. It's whatever shape the material takes is the shape you're stuck with. And I think with Bill, we really fought these shapes, I have to admit. But there's some interesting things going on with his lightweight composites in terms of shape because they're not tensile shapes. Actually, some of them are even compression shapes. So these are carbon crystal sails we did for Miami Basel Design in 2009. And what we did is we just used stock Code 0 shapes from Bill, which had the deepest draft of form he could mold easily, and came up with fiber paths and did a combination of red dyed aramid, gold aramid, and black carbon pattern, and then put, I forget what it is, like 90 million or something Swarovski crystals in the sandwich when we cooked it. So they were like this crazy active surface. And you can see, we had 5 different colors of crystal, clear, red, blue, that gradiated all over the surface of the sail. But again, this is a literal example of cooking these things into a bag. More recently, we did a couple of pieces of hanging furniture with a carbon tape that North Sails has developed. And this, actually, Bill Chrysler molded. Bill also did the structure for the Swarovski sails. But we built a foam mold in the office, oriented the tapes to the mold, and then cooked it in an oven. And what's great about these things, this is the tapes going down on the mold, is that it's both a compression and tensile structure. So, and that's it being cooked in the bag. And that's it in my backyard, one of the prototypes. But what's great is it behaves like a shell when it's unloaded. So, and we did various thicknesses of these, and this chair weighs a lot less than a pound, I think. Maybe this particular one is a little more than a pound. The lightest one is about a pound. And I had myself and Frank and my kids, there were like 4 or 5 of us in this on New Year's Eve late at night and couldn't break it. So we've had close to 900 pounds in it. It's just supported by this little thin string of spectra that's glued into it, but it's super, super strong, but super light. But when it's hanging there in the wind, it holds a shell. The minute you sit in it, you overcome that compression load and it turns into a tension structure. So, but you're not burdened with this whole aesthetic of hanging catenoidal shapes. It's the thing I hate so much about tension, form-finding architecture. Andreas already showed these bricks. I think the thing I want to point out here is just how incredibly light they are. The fountain that kind of inspired all this, and Sylvia kept pushing me towards thinking of these toy furniture things as fountains. This is the one that was at the Hammer, but in both cases, the Hammer fountain and this one that's being dropped into my house about a week ago, the pallet weighs more than the fountain. And to me, that's what's incredible. I mean, you look at the thing in stone, the thing weighs tons. And so now, instead of a thing that weighs tons in stone, you got something that weighs just a few hundred pounds and is hollow, lightweight, transportable. Andreas already left the room, so I can say easily assembled. But it's a very different paradigm. You can still have mass, but you get rid of literal weight. And the reason I like these lumpy forms is they look massive. It has all the characteristics formally of mass and stone. And finally, the kind of last thing I'll show is the use of some very lightweight but easily knocked down temporary pavilions. The Swarovski sails were here, but for HSBC, we did this private lounge, and the private lounge needed to get knocked down and taken back to Basel for reuse. And so we came up with this egg crate system where we could make, windows and openings and things like that, but still a kind of a thick private wall that popped together, in a day with a couple of people. And out of this, we were then hired to do the index pavilions, which the index awards are awards to improve life is what they are. That's their brand, but they're sustainability awards in 5 categories. And previously, they've shipped around over a dozen containers of pavilions for exhibition at design festivals all over the world, and they transport them back and forth from the Pacific back to Europe to the States and back to Europe again. So they realized that even though they were doing things in sustainable materials, the weight and the assembly and the size was eating up all this money in transportation. So we used a very nasty, oil-intensive material called fiber-reinforced plastic, which is what probably half of your cars are made out of now, and built knockdown fiber-reinforced plastic panels that one person can put together a couple of these pavilions in a day. And then the cases for the display of the objects are all Rain-A-Bond foldable aluminum panels with Velcro. So the whole thing packs flat, and we can fit 9 of these pavilions in one shipping container. And this is from Friday. So these are the very first pavilions getting assembled. But like first time out of the box, one person popped them together. So they're super, super lightweight. I mean, one of these one of these pavilions is less than 100 pounds. So we have to fill them with water bags to hold them down. Okay, and then one last thing is just the role of molds in all this and how you use a mold and what a mold suggests in terms of materials. And I think, monolithically, I always thought of if you used a mold, you'd have one material on the mold. And this is actually something Bill manufactured, and it was his idea to use the same mold for 2 different materials. So Bill cut this mold in foam, and then we made these kind of unrolled rings. And within the rings, he cast fiber-reinforced concrete. And between the rings, he cast fiberglass. And then the whole thing comes together. What's nice about it is 2 materials occupy the same surface, which, again, is against a tectonic logic. A tectonic logic would be 2 materials would come together at an intersection. And here, it's one monolithic surface with multiple materials inlaid into it. Then finally, in terms of the ergonomics, that's a rendering of the Bloom house. But in this house, what I wanted to do is take all the furniture and equipment, like the whole kitchen, this office, the powder room, the fireplace, and integrate it all into the walls. Just same as with the Vitra ravioli chair, just suck everything into a surface. So this is a bathroom that's kind of swallowed up all the equipment of the bathroom. So cabinets and vanities and linen closet. And then we slice it, and the slices become mirrored doors for access or Corian. And this was all a fair amount of R&D from DuPont went into forming these panels. And honestly, Pacific Westline in Anaheim really solved most of it in the end. But you can see all the equipment is swallowed up into these bulging surfaces. So you get one monolithic surface that has everything from sinks to toilets to lavatories all sucked into it. And the same thing in the living spaces with the fireplace and bookshelves and stuff in the kitchen. It's all kind of swallowed into these monolithic surfaces. So instead of having furniture in the room swallows the furniture in a surface. And for me, that's at the next scale up, a composite approach to design. It's built with plastic, but it's not really about the materials. It's more about the sensibility of approaches to layering where multiple things all happen on one surface. Okay, thanks.
Thank you, Marcelo, for organizing this really great event. And I also was much inspired by Bill Pearson and North Sales 10, 15 years ago. And that's a continuing inspiration, I think, as their technology keeps developing. So I would like to just present a couple of projects by Testa Weiser. And I've also been asked to briefly introduce the Sire Robotics initiative. Just as an introduction, I'd like to engage some of the larger topic of the conference, but I too am interested in continuity and taping and gluing over a tectonics of assembly. And I'm going to be showing a couple of projects that deal with continuity in different ways. So central to our office's design approach is the concurrent development of logistical, material, formal, spatial, and operational concepts. And I think that's something that we're in a time where maybe the first time in history in which all of those things can happen in some kind of a syncretic process in which these things inform each other. And I think we've seen many examples of that kind of dynamic going on today. And I find very exciting and challenging as a designer. That I think composite materials are particularly open to this kind of syncretic approach in which tunable material properties or qualities and formal systems can search for each other or through a process of maybe conflict or mutual definition, but in some ways some search process that takes place in a nonlinear design and fabrication cycle. So let's see. Sorry. Let's get this. The Automorphic Strand Tower project, which I'd like to just talk about briefly, that's running here in the video, pushes the material and computational investigation that we initiated a long time ago in Carbon Tower to extremes, to explore fiber behavior. So this is less a building than it is a kind of series of studies and investigations into fiber behavior and traits at the widest range of scales from the molar to the macro. And I think that one of the things that's characteristic of this and many of our projects is that an interest that rather than to reduce construction with its situated and complex forms of agency to industrial manufacturing, we would like to pursue and believe that the next generation of manufacturing will look much like construction. From this perspective, construction may be understood as a specific type of production that can be rebooted or retooled to produce new architectural systems. So here in this project that's fiber investigation, fiber behavior and patterning is scripted and iteratively rescripted, computer-generated on a Weaver software platform that we developed several years ago, but continue to use. And the underlying principle of fiber agency and affiliation is more informal and three-dimensional than conventional woven patterns. We use a heuristic in this work that's based on templating or a breeding process to generate a range of fiber behaviors that are sequentially recombined to form a basic fiber group that in turn becomes the template for a specific three-dimensional textile. Through various prototypes like these here, we're exploring the potential of strand patterning and texture at an architectural scale. And the idea here is, in a way, we're not concerned so much with conventional tectonics, that the belief here is that if we throw enough fiber in many directions, and that we'll actually have a viable structure. So that also suggests a kind of interest in an approach that accepts the inexact nature of construction as an opportunity to produce new forms of architecture and new material effects. So the Strand Tower is like a giant textile made up of a series of nested nests. And this system builds strength through relatively weak elements arrayed in massively distributed spun and tangled networks of fiber whose topological complexity and robustness is beyond simple calculation. So through many iterations, we're able to generate the types of patterns and textures we wanted by using ultimately a template that's made up of only 114 strands. So we, in a sense, have a kind of basic building block. This is that's nested and re-nested to produce certain kinds of, let's say, patterning that we're interested in. So some of those behaviors and traits from fraying, bundling, knitting, to bias patterning are all templated into this design. And this template is recursively nested 70 times to yield approximately 8,000 strands that make up this prototype. So in a sense, there's a kind of modular element within this that allows us to produce an enormous variety of fiber conditions, but using a basic building block. And within this also, I think that the point that was raised earlier about materials and material properties, that here we're more interested in the material behavior than in the material itself in this case, because fiber could be of any type here. We could use organic or synthetic fibers. We also, in this project, we're also thinking of this as a form of climate buffer in which hygroscopic materials with fire resistance could create a microclimate within which one could construct any other kind of structural framework or structural type. So it's not, in a sense, a kind of absolute that the entire system would have to be made out of only one building system. I, too, am also interested in the idea that we can combine in several different systems today. So here is our basic fiber group that is exploring different ways in which this, again, is a project in which construction was not a major consideration for us. We did not spend a lot of time thinking about how we would actually put this together, other than the notion that these fiber groups could be isolated and then, as in the first small example, potentially dropped into place, so one could have them through a series of dropping, allow them to begin to nest into each other, or through a kind of thatch approach, either manual or robotic, using pultrusion to form the actual elements, could be built up into this thatched structure. Let's see. Okay, the second project that I'd like to just get into, this is very current and in a way not as developed as I would like it to be at this stage in terms of presenting this work, but it's also, since I realized that I was going to be with boat people, and I'm not a boat person, but I thought I needed to have a water project, that this is a project that we've been working on with NASA. That we were invited by NASA Ames to work with them to develop a series of designs and systems to deal with biofuels and water projects on a global scale. So this is looking at what we're calling Vaporware, or VPR, that involves a series of pilot projects in stressed environments around the world, and also involves production of biofuels for various companies or also the US Navy. So this is a very ambitious project in terms of its scope. There are 4 elements to this. One is biofuels, photosynthetic bioreactors that are ocean-based, and use a biotech microalgae that's been developed by NASA as the basic let's say, fuel source. And the bioreactors in this case are closed bioreactors that use freshwater-based algae within closed environments in the ocean. That is also taking advantage of the ocean to move the algae without any additional energy, other than through harvesting, which I'll show a couple of examples. But what's kind of fascinating to us about these projects is that a lot of the work that we've done over the past 10 years is finding very fast and very direct application in these different projects, in which we're able to actually take advantage of many of the materials and also formal language that we've been working on with strand-based systems seem to quite naturally, or in a way in a quite easy way, find their way into these projects. This is one example of a cross-section through a large bioreactor that is basically a knotted series of tubes, and also in this case involving harvesting and biofuel production at sea on a ship that is able to collect and also distribute these quasi-nomadic groupings of reactors. Again, several different forms are being explored here, from hard to soft. So this is an example of hard manifolds that are, again, closed systems that have to be able to survive in very harsh environments and be able to also be harvested and used for biofuel production, in this case for the US Navy. But as you can see, the material possibilities in these projects are, for us anyway, very exciting and interesting problems that have to do with making materials that are able to be quasi-transparent, but at the same time be highly resistant in the ocean environment. Soft manifolds, so again, we're also looking at these in a series of microenvironments, so in other words, different kinds of ocean conditions, so coastal, open water, estuaries. These are different environments which start to produce different kinds of system logics and material possibilities, including various kinds of aggregations. And also, the second aspect of this project is looking at secondary wastewater treatment and compound recovery. This is for 50 sites off California. There are 50 outfall sites in California that have very poorly treated water. And this is one dimension of this project, as well as looking at how one could use those outfall sites with these massively stranded systems to be able to produce algae as a means of wastewater treatment, and also compound recovery to be able to recover all the pharmaceuticals that are going into the ocean and be able to reuse those as new chemical compounds. This is, again, a whole series of strand-based systems and studies with various kinds of tubes within tubes that are actually using a lot of the technology for tubular systems that's been developed in the medical industry. Then another part of this project is, again, looking at various kinds of braids and tangled systems that are either able to have returns in them so that they can return material back to shore, or be free in the ocean or within a river or estuary. This is now moving into some of the, let's say, prototype and pilot projects. Two of them, one is in Guinea-Bissau, which is a very low-lying part of West Africa that has tidal rivers that go very deep into the country, and looking at that as one type of environment. Another environment, well, actually this is also looking at processing biofuels locally so that one's able to use a series of canisters that are able to be easily transported and produce high-quality fuel. Another dimension to this project is also taking salt water and making fresh water, so desalination, and we've developed a vessel that is able to use the difference in pressure between the ocean surface and 50 meters below the ocean, and therefore does not use additional energy to push the water through filters using, again, nanocomposites, which is a whole nother class of materials that has not been much discussed today, but is opening up very, very interesting possibilities, beginning with new kinds of filters that allow a lot of these water treatment processes to be fundamentally rethought. Another part of this pilot project is on Cape Verde Islands off of West Africa, which is one of the driest places on Earth, and that in this case looking at water harvesting systems that use, again, very microfiltration to produce water from various kinds of collections from the environment. So water vapor, this is on an island that's called Fogu that rises 2,000 meters straight out of the Atlantic, and is an opportunity to explore these kinds of water harvesting systems using strands and hollow fibers that are able to absorb water, and augmenting these land-based systems with air-based harvesters using microporous membranes. So there's an enormous number of material possibilities and experiments in this project. So just to conclude, am I doing okay for time? Is there? Okay. Just to conclude, I'd like to just give a really brief overview of the Sire Robotics Lab, which we're all very excited about, which is an initiative that Devin Weiser and I proposed about a year ago, and it demonstrates Sire-Arc's incredible agility, is that in this 1 year period, we now are in the position where in about a month this lab will be operational. There's a couple of, I think, interesting ideas behind this that are related to a lot of the topics today that have to do with, in this case, looking at new modes of production, and Andreas obviously is a big inspiration to us here on this project. But we're also introducing some different ideas. I think that one of the emphases here is to use small robots and a large number of smaller robots, as opposed to one, or the basic understanding that in construction we're going to focus on using very large robots to lift heavy things. Here, our ideas know that we would be able to pursue a different track altogether and explore collaborative or synchronous robotics in which 2, 3, and in our case up to 5 or 6 robots could actually work together. And this is a kind of throwing out a challenge to all of us in terms of how we might actually be able to develop the programming and control models for these complex interactions. But we've set up this image here is a basic setup in the lab in which we have intersecting work spheres, which basically create the potential for various modes of collaboration among the robots. The other thing that we've also done is we have, as you can see in this image, no end arm tooling. And so we're starting from zero on the end arm tooling, and with the idea that we would like to explore the design and development of end arm tooling as a part of this lab, and to be exploring additive instead of subtractive or at least principally additive manufacturing, looking at fiber composites, but also looking at rheological materials, using deposition and spraying instead of milling. These robots are really lousy at milling. They're not strong enough or rigid enough to do that. So it basically puts us into another set of investigations. The other thing I think that that's fundamental here and important in relation to the topic of materials after materials is that simulation is to be given, or at least in the conception of this laboratory, is given equal importance as any kind of manufacturing. So the idea that we would be simulating materials, and designing various kinds of movement materials, and starting to let them influence each other, so that rather than seeing this as a shop, that we look at this as some other species of laboratory that can begin to start to open up other areas of investigation formally, but also materially. So this is our little lineup of robots. If we could just, I just show one small video clip and then I'll wrap. This is just a clip of pre-commissioning that a group of students has been doing with the smallest robot that's actually in operation here for the past month or so, or 3 weeks. And one of the last point I'd like to make is simply that the types of robots that we're working with here at SCI-Arc have a spherical work envelope, a full 360 sphere, and that's very different, ultimately, subtle, but I think a fundamental difference from the automotive industry robots that are oriented towards a production line. So this is a more, in a sense, a more abstract condition that doesn't necessarily suggest an application. And in the end is also, I think, ultimately a more spatial condition that allows for us to begin to hang robots upside down and on walls. It's also possible with smaller and lighter robots to keep reconfiguring them. Okay, thank you.
So here we are at the end of the day. Most of the heavy lifting's been done. In fact, Lynn did half of my presentation for me. When I was putting this presentation together, there's no way I could have imagined that at the end of a conference attended by architects, people might already be tired of sailing antidotes and sailing boats before I even got up to the podium. But sorry for that. That's all I got, really. I'd like to start by riffing off one of the many lovely comments that Wolfgang made this morning. He said something, I'll paraphrase, something to the effect that when he bought his business, he ended up with a product that was low cost and low sex. And at North Sales, we're kind of exactly at the opposite side of that spectrum. And to a degree, in our business, it's a case of maybe you can buy better, but you can't spend more money. I think it will come as, and people reckon the sex appeal of sailboats to be high on occasion too. So I think it will come as no surprise to anybody in this room that when we're talking about applications for performance sport, composites are the norm. In fact, it's a rare instance for a performance sport application where an item would be built of anything else but composites. The reason for that is in performance sport, whether it be motorsport, sailing, or cycling, there's an insatiable demand for more stiffness and less weight. In fact, in the sporting world, the sort of generational product cycle is roughly 1 year. And everybody expects that their Formula One racing car next year, their new sailboat next year, or their new sail will be lighter and stiffer than the one they bought this year. And they're a little bit disappointed if you haven't made a little bit of progress in both those areas. So it's kind of both at the same time, please. So this creates an environment where there's a lot of pressure for development and rapid development, and there's an appetite for early adoption of new materials, sometimes for better, sometimes for worse, but that's the environment we live in. And it also creates a little bit of a tolerance to some degree for failure, or at least for, okay, it wasn't perfect, but it was good enough. And I know that's an environment that's completely unacceptable in your business. And, you know, in that regard, we're a little bit unique. And also, as Kurt Jordan was saying this morning, there is, you know, we have the privilege to operate in an environment where people will pay a significant amount of money for a perceived competitive advantage. So in North Sales, we started down our route in the composites world in the early 1990s, just about 20 years ago, when we developed a process for manufacturing yacht sails in one piece, full size, on large articulating adjustable molds. So previous to that, sails were, traditional sails were made out of woven materials. So material was woven in a textile mill. It came to the sail maker on a roll as roll goods. You cut out sections, or as we call panels, you shaped them, and you joined them together mechanically. So mechanically in the textile business is basically stitching. It's the textile industry's version of the screws and bolts Greg was talking about. And if you needed more strength or more modulus on a certain part of the surface, you basically stacked on layer after layer of the same material and mechanically fastened it. So to use your terminology, traditional sails were effectively tectonic. Today, modern performance sails are what I refer to as flexible composites. It was a little bit of an oxymoron maybe to a composites engineer. But they have some properties of textiles. They're somewhat soft, they're flexible and foldable, but they're made of the same materials, more or less using the same processes that the rigid composites industry uses. So you can see in the sail plan there that the fiber orientations and trajectories and the greatest densities are clustered in the corners on sails from where the loads are reacted. This is a photograph of a boat that weighs about 240 tons. It's 150 feet long. The mainsail at the back of the boat is about 450 square meters or so. In the body of the sail, in the more lightly shaded areas where the loads are dispersed, the laminate is barely 2 millimeters thick. In the clew corner down here, the highest loaded part of the sail, the laminate's maybe 35 or 40 millimeters thick. So an inch and a half, more or less solid block of fiber and resin down there in a corner. The fibers fan out continuously from the corner and disperse over the surface as the loads dissipate further into the structure. So modern sail design starts with a finite element analysis to look at the fiber strain of a particular sail geometry. From here, the sail designer decides how much fiber he needs in the structure and where to put it. And there's a photograph of a relatively simple fiber architecture for sails for a small boat. Again, these are sails that are made in one piece, molded in our factory. And you can see that in modern sails, the fiber orientations are asymmetric. And asymmetry is good, or is effective, both in terms of performance and in terms of material economy. So as opposed to, for instance, a formal symmetrical microstructure of a textile up there. So we place the fibers in sails in locations of anticipation of the wind loadings and variations in the stress field as the boat moves through the waves. So by using different orientations and densities and trajectories, we're able to optimize locally for strength and stiffness in different parts of the sail. So we put the fiber in only where it's required on an as-needed basis, and it allows us to make the lightest possible structure for any given application. So this is a photograph of the factory, and that So that's a three-dimensional mold there that's adjustable. And the fiber's laid corner to corner over the surface of the mold. There's no seams or joins. So in this, this manufacturing technique, there's no longer any distinction between the sailcloth and the sail. They're both manufactured at the same time. They're inseparable. There's a little bit of a distinction still between the surface and the structure. You can see the fiber architecture is very well defined, but the surface and the structure are put together at the same time, so they're inseparable, even though the structure is still visible and distinct from the surface. It's a sort of an end-on view of these adjustable molds. So there's a flexible, deformable surface that's inflated or lowered with these pantograph lifting mechanisms. An underside, a view underneath the same tool. So that tool's got a surface area of about 500 square meters. It's 48 meters long. It's 19.5 meters wide at the base. And there's about 240 of these lifting mechanisms underneath the surface to adjust the shape on a bespoke basis, sale for sale. The way these lifters are moved is these two pneumatic actuators here attached to a vertical screw. So the level of accuracy in the Z direction is effectively a quarter rotation of that screw. So it's inside a millimeter up and down in the Z direction. So it's a fairly accurate adjustment for such a large platform. It's an overview of the factory. There's overhead gantries are running the length of the shop, and there's 11 different adjustable molds to handle sails of different sizes and geometries. There's a robotic arm that travels along the length of the gantry and up and down in the Z direction, to which we attach a number of different tools used in the manufacture of the sail, the most important of which is the fiber placement head you see there, which hangs off the gantry, and it's a computer-controlled 6-axis head. Draws the fiber architecture on the surface of the sail in predetermined places to anticipate the wind loads. So that head is following the three-dimensional curved surface of the mold exactly. And there you can see the fiber architecture from the corner. You can see all the load paths running down in the corner, and the fiber fans out in more or less catenary curves across the surface. And we build a vacuum bag around all the laid up materials, draw 1 atmosphere of pressure, and then heat the laminate up with an infrared heating device that travels over the surface of the membrane. It's a thermoplastic adhesive, so as soon as you remove the heat, it sets up pretty much instantly, and you pull off a one-piece molded sail with a three-dimensional shape molded into it, even though it's a flexible laminate. So that process is 20 years old now, roughly, so it's a little bit long in the tooth. We spent the last couple years working hard on what we hope is going to be the next generation of performance sails. We've started recently building sails out of pre-preg unidirectional tapes as opposed to the yarns or the fiber tows you saw being laid up in photographs of the process. So this is nothing new in the carbon fiber composites industry. This is the way high performance parts are made, but in the flexible composites business, this is quite new. So we're taking a yarn tow or tape, which is made up of individual filaments. We're spreading them out in a straight line, impregnating it with resin, and we're going to lay up sails that no longer have any film or any substrate on them. So a sail in the future will be like any other composite structure, will be only fiber and resin. These, because of the nature of our process and because things need to be very light, we've created our own system for making those pre-preg tapes. They're a lot lighter than is available anywhere commercially currently. And because they're so light in gossamer, you can't handle them by hand at all, so we had to, again, develop the robotics and the machinery to deploy these pre-preg tapes. So there's an example of a ATL system, or automated tape laying head. And instead of applying the tapes directly onto the molds as we were doing with the fiber load path sails, we plot them out in sections. In the composites business, this is called a preform. So you plot all the materials out in sections, and then you move it over to the mold. So a whole section will be plotted out with all the different orientations and densities, and then the sections will be brought over the mold and vacuum bagged and cooked the way you saw the 3DL sails work. And there's been way too many photographs of the Alinghi boat project today, but here we have another one. This is one of the most technologically advanced sailboat programs in the last few years. And on the boat here, you can see in the darker sail on the front is one of these fiber composite sails I'm talking about. The sail is just completely fiber and resin. And the main sail on the boat is on a load path 3DL molded sails that I just showed you the process for. So the interesting thing here is that this is what we call a load path structure, and the new fiber composite sail is quasi-isotropic. So there's no distinction anymore with this sail between the surface and the structure. They're one and the same, and they're completely inseparable. And you've already seen a picture of this. As Greg talked about this. This is a project conceived by Greg and built by Bill Chrysler using our sail materials, this new material. And the only thing I'll say about this that Greg didn't say is this exists in an interesting space of intersection between composites and textiles. So this has got a lot of characteristics of a textile. It's foldable, you can roll it, it's soft, but it's built like a composite, and it retains its molded in shape there. And as Greg was saying, this weighs roughly a pound, and it can easily hold roughly 1,000 times its weight. You know, it's incredibly strong. I'll move through this quickly. This is a process we developed a few years ago that we don't in fact use anymore, but I think it's interesting for this group of people here because it talks a little bit about doing these bespoke processes on scale. So we call these rotary molded sails, and all these sequential manufacturing processes I showed you earlier on the molded sails are performed on this drum simultaneously. So this drum would rotate here. There are actuators inside the drum that would fire a piston through the surface and deform the surface while the drum was rotating, and the materials would be fed into the drum, and out the backside would come a connected stream of three-dimensionally molded laminated sails. All the sails would be different shapes because the drum would change its shape as it turned. So there's a close-up look at the drum. So there's a film substrate on the drum. The drum is moving, and these fiber placement heads are traveling back across and forth across the surface of that drum. And there's a close-up, so you can see there's aramid fiber here being laid down through this head, and that surface is actually, you can't really see it, but that surface is deformed into a three-dimensional aerodynamic shape. And as the drum moves, the heads travel back and forth, and the surface of the drum is continually deforming. So a sail is a different shape at the top and the bottom, so the drum continuously deforms as it turns. This one there, okay, there's this, to just give you an idea of the scale, that's a 12-meter drum, and you can see the holes in the drum there that the actuators would fire pistons through. And that's kind of a look inside the drum. I think there's 2,600 actuators would fire pistons through the surface to deform the surface of the drum into an aerodynamic shape. So we're not using that anymore for a variety of reasons, but we did sell one to Boeing 7 or 8 years ago. And just quickly shoot through this, but we're using the same process to also do epoxy matrix rigid composites. We own a mass building company and a boat building company, and so we're deploying our ultra thin pre-preg with our automatic tape laying, and these are pre-preg sections that are going to be laid into a mold to build a mast for a racing sailboat. And we've also, we're starting to promote some of this technology outside our own business, and we're involved with a company in Switzerland that's making skis with these materials. And we're also involved with an around-the-world airplane project called the Solar Impulse, where they're going to be the first, hopefully the first plane to fly around the world with using only solar energy, and we're going to be supplying our ultra-thin prepreg materials for that project as well. That's a 60-meter prototype plane, and the real deal is going to be 80-meter wingspan. And quickly, do I got time to do my video? I've got a little. If you're not tired of sailing, I've got a 4-minute video that I'd like to show you just because it shows a little bit of the scale of the plant, and there's been a lot of talk about mass customization over the course of the day here, and mass customization is exactly our business. The process is the same, but each sail is unique in that it's got its own geometry, it's got its own structure, and it's got its own aerodynamic. Pause for a second. Is this it? So I'll just say at the start, the sailing portion of the video, the noise you hear is simply the noise of a very stiff, rigid carbon fiber structure moving through the ocean at high speeds. And if you think it's unbearable, it nearly is. Thank you.
Well, thank you all. That was pretty inspiring. I feel like I'm sitting at this sort of intersection of, the sort of pop sensibilities that Greg brings to some of this with really, really, really state-of-the-art performance ideas that will help to kind of enact many of the kind of visions that Greg has. So it's a pretty interesting confluence of, real world operations and, imaginative design. And the idea that I'd like to put to you, and I've been wondering about all day really, is here we are with state-of-the-art, performance-driven, cost is no object, technology. And I'm wondering if any of you can see a kind of trickle down into an arena where these efficiencies, which everyone has been talking about, and these deployments of materials and minimal structures can trickle down into the real world and have an effect there. Anybody want to lead off?
Well, I think, the two projects that Greg and I did do together speaks exactly to that. They're experimental, and it's always a little bit tricky doing something that hasn't been done before, but that was exactly the idea, particularly in doing that chair, is trying to investigate whether there would be any trickle-down effect, which we talk about a lot in our business, and to sort of investigate how practical it would be to do that on a larger scale, for instance, for furniture design or industrial design.
Mm-hmm.
Yeah. And I think the furniture industry has these incredible markups on production costs that have to do with storing furniture, shipping furniture, warehousing it. I mean, it's ridiculous how little it costs to make a chair, but once it's in the showroom, it's at least 400% above the manufacturing costs, all because of these things. And even though that chair's a prototype, it's not really meant as a commercial product, but something like that can, more or less just like fit in your backpack and crumple up and ship to somebody in a FedEx pack. I mean, you could buy a chair and instead of having a giant box with a mover, you just get a letter size envelope and hang it up. And same thing when you talk to a manufacturer and they say, well, that material looks expensive. I mean, now what I tell them is it's more expensive than diamonds, but it's so light and there's so little of it, it doesn't really cost that much. So, I think if you were gonna make like a table like this out of it, it's crazy. But if you're gonna use it for what it's good at, which is lightweight, it's actually not so unobtainable,
I'm also struck by the fact that so many of the things you're all talking about are, sort of manufactured without a heavy investment in molds, and there's a heavy investment in equipment to make a constantly variable mold. But how quickly does that get amortized into the product?
Well,
Too tough?
I don't know, reasonably quickly. If, the thing about industrial investment on that scale is that you have to keep the machinery running. So that plant runs 24 hours a day, 7 days a week. And as long as you have enough business to support a hungry beast like that, the economics work very well. However, that level of investment you need to keep the machinery running all the time to get your investment back. But I thought you were going to make a different point about just, we own a building company, so we understand what the cost of building hard molds is to make composite parts, and it's a significant part of the cost of a composite item is the mold, yeah.
Well, there were, I think in the 60s, and Peter, you may know better than I remember some bobbin wound proposals for housing out of fiberglass.
Yeah.
And your bobbin seemed to me to be, an ideal kind of vessel to do something like that.
Yeah, I think this question about the molds, I think, is a really critical question, especially scaling up to any kind of architectural application. That pultrusion, which is a technology that we focused on, offers a way around the mold altogether, because you're basically pulling fibers through a die, so you don't have a mold. So that I think any areas of free-form fabrication really are, I think, one critical dimension of moving into fiber technology towards doing away with molds, or at least finding ways to use molds less and less.
Is that when you were talking about the robot lab?
Yeah, that's one area of really pursuing not using molds, or at least to set that up as a challenge. The other area, I think, in terms of finding large applications, I think these infrastructure projects, we're talking about, hundreds of kilometers of tubes, that once you start doing something like that, you can start to amortize sophisticated equipment like some of the things that they developed with this tubular setup at North Sales. And also the other way around molds is inflatable rigidizables, where you take a pre-preg and then inflate it, and then it becomes rigid, which is one of the things that actually a technology that NASA developed a long time ago for space applications, so that you would have a very small payload, you take it up in space and inflate it, and it becomes hard. It's basically just resin it's chemistry in terms of temperature settings in resins. And that's also a technique in the bioreactors that we're working on that would allow us to do things without molds. Does have limitations, of course, in terms of form, because you have to deal with some of the things that others have been talking about in terms of inflated structures. But there are, I think, various kinds of techniques to deal with getting around the molds.
Well, Greg said that he hated tensile structures, but an inflated structure like your chair.
Yeah, but if you were to put fibers into it, you can get an inflatable structure that's not inflating based on uniform pressure.
Right, that's
I think
not platonic, yeah.
Yeah.
Go into that further. I'm sure everybody.
Well, no, it's just that what Bill is doing, because the sails need what they call a flying shape, which has nothing to do with the hanging shape of the membrane. Where the fibers are and how it's cooked is what makes it have that shape. So instead of just, I remember when Burrow Happold was showing me their rolling ball simulations and stuff to give you tensile shapes, I was always saying, like, what can we do to get rid of that silly chimney shape? And all they could do is, change the perimeter or change where the hole is, and they're all excited about the form finding, but form finding is a paradigm that comes from the 60s. I think this paradigm now is these isotropic structures, which are quasi-tensile, quasi-rigid, and it seems to have a lot of applications in the building industry in a lot of ways. I mean, the other thing that I think was great is when Wolfgang was saying, I want to get these things on the site, I think our industry, unlike a lot of these industries, has the people digging in the ground. I mean, it's a totally medieval kind of a workflow versus, when the Corian from DuPont comes in, that's a totally, factory-based workflow. And bringing some of this technology on the site, even if it's an inflatable, mold for a foundation or something, would be really great. Because I think we, in the building industry, we have to juggle 2,000-year-old technology and state-of-the-art technology in a way that in the boat industry, they don't have to deal with that antiquated stuff.
Right.
And because of the job site, we're really stuck with a lot of people with shovels and backhoes and plywood formwork and stuff. It'd be nice to upgrade a little bit.
It's about time.
Yeah.
Well, you've done a lot of work on that theoretically, right, Peter, to bring the manufacturing right out.
Bring it onto the site, and material production, actually, with fiber technology, there's, I think the option, like Greg's chair, of being able to have pre-preg materials that you can actually roll up, which means that you would have much less transport volume, bulk, and weight, which is clearly a big factor in terms of energy in any construction site, but also much more variability, because you could do some of the kinds of things that they're doing either off-site and then pre-preg them and roll them, or actually produce things on-site using various kinds of robotic fabrication techniques. So I think that there's many, many options that haven't been explored yet. So we're at a really great time, I think, to be a designer, if we can begin to start to find ways to crash out of this situation that we find ourselves in for about 50, 60 years, yeah.
Well, I don't know if you're all feeling the same way I'm feeling, but I'm feeling there was a tremendous synergy in the way this conference was organized. I can just feel almost a woven, texture. It's almost like one of your sales, Bill, where I think a lot of the connections and information that we've all received is going to gel over the next few months or maybe years. And I'd like to thank the three of you very much for.
I mean, the one thing nobody
Oh,
said,
go
although,
ahead.
just to wrap up, I mean, software is a huge part of this.
Oh, you're
Yeah.
right. That's right.
I mean, build and show. I mean, a lot of people didn't show
But he
software.
had a hand there, though.
No, they have massive, when I look on their website, they have more software products than sale products. I mean, tons of research into modeling and manufacturing, which is, I mean, the one thing I think about all this stuff today, that's a little bit the uncharted territory, is the software that lets you go from what's on your desk to talking to the robots.
Yeah.
And that's a huge, there's no uniform standard for that. Every robot's a little different. I think that's where a lot of the action's going to be in terms of design and manufacturing. It's not so much in the hardware, it's in how the software talks to the way you design and the way you manufacture, which in Bill's industry, it's a closed loop. In our industry, it's a total wreck.
Yeah.
I mean, unless I don't know something.
No, you don't.
No.
You know
It's a
something.
wreck. It's a wreck. But I think we should wrap up, and I think Devin's going to give us some final words. Thank you.